Welcome to my new calculus channel. My name is Gabriel. In this video I'm going to show you how to prove the so-called fifth postulate. It's not really a postulate because it can be proved, and I'm going to show you how to prove it, and you'll be surprised that this is being touted as one of the theorems or statements in the Euclidean elements that had no proof whatsoever. And the first idiot to mention this was Proclus, but in fact it can be proved, and I'm going to show you exactly how to prove the fifth postulate by making no assumptions about anything. Okay, so the first thing we need to do is we need to actually define parallel lines. Okay, so let's do that. We can start off with a circle like that and draw two tangents to the circle. So we can have, let's say, a tangent like that, and just copy that. Whoops. Wait a minute. Let's move it there, and let's say, let's get another tangent here. Okay, over here. So it goes over there like that. Okay, so now we're going to define lines, these two lines, to be parallel if the co-interior angles of, first of all, we're going to draw a transversal, and this line here is going to be the transversal. So we're going to say lines are parallel if the transversal that cuts the lines cuts them, and the result is that the sum of the co-interior angles on either side is 180, or two right angles, right? So we'll say these two lines are parallel if the sum of these two angles is the same as two right angles. Okay, two right angles. So two right angles tell us that these lines here must be parallel. And you may say, okay, well, how do we know that this is one right angle and this is one right angle? And that's pretty easy, because if we, well, let me just redo that. If we have a diameter like that, okay, if you have a diameter like that, we know that this transversal is a perpendicular bisector of the diameter, and all we have to do is just continue moving it until it becomes a tangent. It doesn't really become a tangent, but until it coincides with the tangent line, and hence we know that that has to be 90 degrees also. Okay, so that part is taken care of. Yes? Okay. So the first thing is we define lines to be parallel if the co-interior angles, on either side of the transversal are equal to two right angles. Okay, so that's the first step. That's step one, right? Step two, from this we can easily prove that the sum of angles in a triangle is 180. Okay, so, well, we've got our two parallel lines like that, yes, and we can draw a triangle like this, and the proof will follow pretty easily, because we know that this angle is equal to that angle, this angle is equal to that angle, and since these three angles here are 180, it follows that the sum of the angles in a triangle must be 180 degrees. So we know that the sum of angles in triangle is equal to two right angles. Okay? And the third part that we're going to concentrate on is this. It's actually something which you probably never heard of before. Number three, it states that if you are given any two lines like that and like that, which are not parallel, okay, any two lines which are not parallel, and you pass transversal through them, what this theorem states, and I'll call it the Gabriel theorem because nobody ever bothered to give it any attention, or if they did notice it, they didn't really realize the significance of it. But in this particular case, you will notice this theorem says that the sum of the co-interior angles on either side of the transversal is always the same, no matter how you move this transversal over these two non-parallel lines. So to give you an example of that, if we take a look at this here and we just, do this with the lines, something like that. Okay, let's just go like that and like that. Okay, now these two angles here always have the same sum, regardless of how you move the transversal. Okay, they're always equal to, in this case, 145.62 degrees. So we know that, don't we? Right. So once we've figured out this part of the proof, that is, that a transversal falling on two non-parallel lines will result in a sum of co-interior angles that is the same no matter where this transversal is placed over these two lines. Okay, so no matter where it is placed here, it will be the same. This sum will stay constant no matter how it is moved. So again, to illustrate that fact, if we do this, watch, this particular sum up here doesn't change. Yes, it stays the same. Okay, and would you believe it? That's pretty much it. The only part that's left now is the last part, which is number 4. And in number 4, all we have to do is say that given any two non-parallel lines like this, okay, any two non-parallel lines like this, they will meet. So let's say we haven't drawn this part yet. These two non-parallel lines will meet at some point E over here. Okay. Since the sides of this triangle and the transversal are the sides of a triangle, and we already know that the angles in a triangle must be 180 degrees, right? So the only way that we can tell for sure that these two lines will meet is the fact that the sum of these two co-interior angles is less than 180 degrees, or less than two right angles. Yes? And so that pretty much proves the so-called fifth postulate. It's not a postulate. It's a very stable and well-known theorem. The fools that came before me never realized this, didn't even get close to realizing it, and I'm telling you right now that it's neither a postulate nor an axiom, and it can be proved, and this is what the video is about. So you can actually look at this applet that I've demonstrated to you these facts, and also note that if we extend either of these two non-parallel lines like so, that they will meet on the circle, on the same circle that passes through these 3 points. Okay, so it doesn't matter what these 3 points are, the circle will pass through the 3 points plus the point where the two lines coincide. And that is pretty much all there is to claim number 5, not postulate number 5, but claim number 5. This is the New Calculus channel. I'm John Gabriel. Till next time, goodbye.